Hello, everybody. Welcome to Lesson 7.3 on special exponential functions. Today's goal, we're going to be analyzing expressions and functions involving the natural base e. So this thing, natural base e, this may be something that you've heard of before, maybe, may not. You may have seen it before, just kind of like e italicized, on its side. This is a very special number in math. It's a special number in the same way that pi is a special number. If you've watched the previous videos, if you watched the first couple of videos about E, you should kind of have a sense of it so far. But here's kind of a summary, here's a comparison. So there's a number that we all know, pi, 3.1415, so on and so on. It is a number that describes something that is true about just reality as we can see it. When you see a circle, the outside of that circle is always 3.14, so on and so forth, times bigger than the distance across. So if I take that distance across the circle and I wrap it around, it'll take me like 3 and a little bit more to get around. Doesn't matter if it's the smallest circle in the world, if it's a single atom, or if it's, Jupiter. Doesn't matter. As long as you have a circle or a sphere, the circumference around it will be 3.14 times the size of the diameter. Okay, so that is just an essential truth about reality. That's an essential truth about what it means to be a round shape. E is similar. So E is not so easy to describe. However, it is similar. It's a number. It's a constant. It is a certain number that exists that has a fundamental meaning in the world. And for me, it's a lot harder to describe what that meaning is, especially compared to pi. Pi makes sense to me. It's just, the outside's 3 times bigger than it is across. Very short and sweet summary. With E, it's not really quite the same. Now, what I can show you a few things. So first of all, where does E come from? So this was already shown in the other videos, but when you take this particular equation, 1 plus 1 over n to the nth power, and you let n get bigger and bigger and bigger, you approach the value for e. So it's the value for e is like 2.72-ish, 2.718, I think is what people usually will read out as the first 4 digits. So this would be like you have something. Let's just go through the numbers. So like you have something and you double it. So let's say n is 1. So 1 plus 1, you're doubling it, and you do that 1 time. Okay, so you get twice as big. Now, what if we make that a 2? All right, well, I'm only adding half as much, but I'm going to have that happen twice, and it's going to be multiplied, right? It's going to be to the 2nd power now. So I'm going to take my 1, I'm going to turn it into 1.5, and then I'm going to multiply it by 1.5. So when I do that, let me see what we get for n equals 2. We get 2.25. As we go on, as we say, I'm going to add a third, and then I'm going to multiply that total by itself 3 times. I'm going to cube it. We get 2.37, so on and so forth. As we move out, we approach a certain number, 2.718. Now, this number has a lot to do with kind of what it says here on the Canvas page, proportional growth. I don't know if that's the only thing that we can tie it to. I would venture to say that there's different ways that you could approach describing this number and kind of what effect it has, what topics it relates to well. But one thing it definitely relates to well is proportional growth. Now, when I say proportional growth, I mean something that grows faster when there's more of it, or possibly grows slower when there's more of it. As long as the amount of something is an influence on the rate at which that thing changes, we call it proportional. So here's some common examples. Animal populations. If you have a bunch of rabbits, let's say, the more rabbits there are, the faster they can make more rabbits. Then there's more rabbits, and the faster they can make more rabbits. And it kind of goes, assuming there's enough stuff to feed them all and there's no predators, then that would be a population that would be growing proportional to their own size. Money is something the same, right? If you don't have a lot of money, it's hard to make a lot of money. If you have a lot of money, it's not very hard to make a lot of money. One of the reasons why is interest. Aside from opportunities of what you can do with your money, simply just interest. When you put your money in a bank, and they sometimes will take your money and loan it to other people for the privilege of you being somebody who has given them money to loan out, they give you interest. That's the deal with the bank. So the more money you have, the more interest your bank pays. Well, the more they pay, therefore your total gets bigger, and the next time they pay you interest, they're going to give you more interest than last time. So the rate at which your earnings are increasing, that interest payment is getting bigger and bigger and bigger as time goes on, because those interest payments are making your total sum in the bank bigger. So you get bigger interest payments. So it kind of, continuously compounds that way. Right now, we're dealing with a big virus, so the more people who become infected, the faster that virus will be able to spread, right? If you have more people with it, the faster it can spread to more people. Radioactive decay. So radioactive materials are materials that are breaking apart. They're kind of unstable atoms that want to break into either 2 or 3 kind of daughter atoms that will be a little bit more stable. Now, the more of that's happening, so let's say we have 2 radioactive particles. Now, one of those can break apart, and it might hit the other one and cause that one to break apart. Now think about if we have 100 radioactive particles, that one particle that breaks apart has a much better chance of hitting one of those other 99, which then have a pretty good chance of hitting one of those other 98, so on and so forth. So the more radioactive material that you have, the faster the chain reaction goes that causes that radioactive material to fall apart. So if you have a big amount of radioactive waste, it will very quickly fall apart. And then once there's a little bit left, that little bit will last for a long time. Okay, so these are all examples of proportional growth. Now, what is Euler's number? Or sorry, Euler's. I pronounce that wrong sometimes. Euler's number, very, very famous. Probably I think the second most famous number in maths, aside from pi and from our counting numbers, is Euler's number. So Euler's number is interesting. If we look at this graph real quick, there's a few things on here. One of them, the red line, is e to the x. It's Euler's number raised to a variable. So we're going to see e to the first power, e to the second, e to the third. So e to the 0 right here would be 1. E to the first power would be should be our 2.17 number, right? Somewhere around there. When x is 1, yep, 2.718. Okay, e to the second would be that number squared. Okay, so we'd be up here at 7 point something. When we look at this line right here, the slope of that line is constantly changing. Okay, the slope of that line starts out positive, but really small, and as we go on, it gets more and more positive. Now, when we do any general kind of any general kind of power, so let's just say a to the x. So we've got some value to the x. Now I've got a little slider I can change what that value is, so we can see that. Let's go through here. We can see that when our base is less than 1, we get exponential decay. When our base is greater than 1, we get exponential growth. And the bigger that base is, the faster it grows, right? That makes sense. If we have 5, and then we do squared, 5 cubed, 5 to the 4th, those values are all going to be a lot bigger than 1.1 squared, 1.1 to the 3rd to the 4th. So as this gets bigger, we get these bigger and bigger slopes. As it gets smaller, the slopes increase, but they become negative. And they kind of bottom out at 0. So we don't have anything, our domain is limited to x values 0 and up. Okay, now, if I wanted to look at 2 to the x, I'm going to kind of give you a preview on some calculus ideas, because E has a lot to do with calculus, as it turns out. So this is kind of a preview for some calculus. If I did 2 to the x, and and I wanted to know what the slope was along that line. Well, the slope's always changing, right? But the slope itself is always going to be let me do something different. Sorry. Let's do x squared. Well, no, let's go back. Anyways, 2dx. So if I want to figure out what the slope is, I have to do something called taking the derivative. Now, the derivative of this, the way that it's written out symbolically, is we use this. This just stands for the slope of the line, basically. When we say the derivative of something, we're really talking about what is the slope of that thing. Okay, so we find that the slope of the line, let's change the colors here, that's terrible. How do I do that? Sorry for figuring this out on your guys' time. Well, anyways, it's the thick red line. So the slope right here appears to be 0.693. The slope, of this line right here, if I was going to make a tangent line, if I was going to make a line that just touched it right there for an instant and showed me what that instantaneous slope was, what the slope was right at that point. At that point, the slope it's gotten a little bigger. It's now 1.029. If I want to know what the slope is right here, slope of a line going like that, then the value is 2. Okay, so these slopes keep getting bigger. Now, let me try to type something else out. If I do a to the x, and I say I want to see the derivative of a to the x, and then we're going to add a little slider so we can say for lots of different bases. So we'll say 2 to the x, or 3 to the x, or 4 to the x. And what you'll see is that as I get larger and larger on my a value, the slope, okay, this line here, which is representing what the slope of this line is equal to at any given time. So once again, at this point, the slope of this line is 0.51. As we increase the value of the base, those things approach each other, and eventually they cross over. So if I go to 3.7, now the slope is even larger than whatever value I'm looking at the time. Now, if you ask yourself, where are they crossing over? You'll find that they're crossing over exactly at e to the x. Okay, so what this means is that e to the x is a function whose derivative, whose slope is always equal to the value that e to the x is. So an example of what that meant. If you have e to the x, and I look at, let's go over here to, okay, when x is 1.8, e to the x is 6.05. The slope of this line right here is 6.05 at this point. The slope of this line is 4.07. The slope of the line here is 2.1. The slope down here is 0.2. If we keep going, the slope will get closer and closer to 0. So e to the x is the only function that exists whose derivative, whose slope is always equal to the value of the original function. Not only that, an additional thing, if I go out to here and I say, all right, at x equals 1, right, e to the first power, my slope here is 2.718. And if I was to drop a line down and try to measure the area under this curve, well, wouldn't you guess it? It's also 2.18. So e to the x kind of goes in two different directions. The slope is identical to the value along the curve, and we call it the integral. The area under the curve is also that value. So it's just this really peculiar number that is entirely proportional to itself. So this is what I kind of meant when I'm trying to tie into that proportionality idea. The rate at which this line is growing is exactly the value at that point. So, for example, like right here at x equals 1.39, this graph is growing with a slope of 4.015, but it's also at a value of 4.015. So it's exactly proportional. Whereas other ones, so like 2 to the x, what you end up doing is whatever the value is, the slope is twice that. I might have that backwards. I think that's x squared. So like if you have x squared and you want to know what the slope is at 3, well, you take 3 and you double it, and that's the slope. So all the other ones are proportional, but e to the x is the only one that's exactly proportional. So no matter where I'm at, the value, like let's just say this was viruses or something. So this is saying that like if I have let's say 4 million cases, my rate is also 4 million cases. Now that'd be terrible. It would go on forever and we'd all get sick. But anyways, that's kind of the main gist of e to the x. In a really limited, quick kind of summary, it's just this special number that has these special properties. These special properties really apply well in calculus. I saw them in chemistry in my senior year of chemistry classes. We did formulas that were supposed to represent the wave function of particles. So it was supposed to be like, okay, we're talking about some electron that circles an atom. Where are all the regions we expect to find it? Well, the equations you use to figure out that kind of stuff in quantum mechanics, you use an equation like this: e to the ix equals cosine x plus I sine x. So you see that we have some i's in there. We have some imaginary numbers, which if you can think back to it and remember it all, I mentioned in a lesson about imaginary numbers that they represent like cycles really well. They do a good job of representing turning motions when you kind of set up a certain graph system. And those turnings, those rotations or cycles or whatever you want to call them, are similar to the waves that describe matter once you get into quantum mechanics. So anyways, all I'm saying is that these e's, they pop up in places. So I saw them in a chemistry class and I just thought to myself, like, why is that there? For both of these, I was like, why is E here and why is I here? I didn't have enough math background to really understand what these things were and how they kind of fit into practical applications in math. But they show up in places, and they show up in some really interesting places. And if you don't understand how to work with them, or like if you don't really have a loose understanding of what they are, it can be really hard to move forward in other places. It won't show up very much this year, so this is kind of just an introduction to the number, to the concept. We won't build off of it too much. We'll see a little bit in logarithms, which is our next module. But for now, we're just kind of doing an introduction. So let me finish reading through the learn section here. The constant e has certain mathematical properties that make it a convenient base for exponential functions. E is the irrational number, meaning a number that never ends, that 1 plus 1 over n to the n approaches as n approaches infinity. So as n gets bigger and bigger, we approach this number. Graphs of exponential functions with base e display the same general characteristics as other exponential functions, such as there is an asymptote of y equals 0 as we go towards negative infinity with x. That's just talking about this asymptote right here, right? Y equals 0 as we go out to the left. Maybe I need to point that way for you guys. F of x approaches infinity as x approaches infinity, right? As we go out to the right, the function goes up. And finally, the y-intercept is 1, right? Anything to the 0th power. So if you take something, put it to the 0th power, you always get 1. Okay, so it shares all of those characteristics. It just also has its own special things. One place where it's really used often, where we're going to do some examples with it, is in compounding interest. So when lenders offer interest rates. Sometimes they do it annually, biannually, quarterly, but you can also do it continuously. And typically, continuously compounding interest is the best way to go if it's available. It creates the biggest changes in the end. So there's a certain formula, A equals P e to the RT, that we can use, where A is the amount in the account after T years. So we're going to say like, and P is the principal amount invested. So if I had $1,000 in my account and I had 10 years, then this would tell me what I'm going to get at the end of that 10 years with that continuously compounding interest. If you have watched the other videos in here, especially this first one, you'll have an idea of what that means. Continually compounding just means that you're compounding basically as much as possible. You're getting interest payments every moment, like every millisecond or half a millisecond. It's an infinitely small amount of time goes by, and you get your next little tiny interest payment. But because you've already gotten a little bit more money from that interest payment, your next interest payment is a little bit bigger. And then your next interest payment is a little bit bigger. And those interest payments get bigger faster that way, rather than waiting a long time to do a bunch at once. Okay, so we will look at example 1 in the next video.